So if you want to calculate moment of inertia of a more complicated object, like let's say you have, let's say you've got this wheel, a hollow wheel. So the mass is concentrated at the outer edge. So let's say this object has mass, let's say capital M, mass of the wheel is 5 kilograms. That's all at a radial distance of, let's say, 2 meters from the pivot point. But then let's say you also have some other object. Presumably this is on spokes. We've got these thin spokes that contribute very little to the weight. But let's say you attach some extra weights to some of those spokes. Let's say 1 meter away from the pivot point, you attach a couple of heavy masses that are, let's say, 6 kilograms each. And those are each 1 meter away from the pivot point. 1 meter away from that axle. But if this is all attached together, then it's all going to be rotating together as well. So as the wheel spins, these two masses spin with it. If we want to find the total moment of inertia, we're going to need to combine these together. So moment of inertia of the wheel, this outer rim, we can calculate using the usual mr squared formula, because all 5 kilograms is that same 2 meter distance from the pivot point. So 5 kilograms times 2 meters squared. 5 times 4 would be 20, so 20 kilogram meters squared. But what about each of these blocks? How would we calculate the moment of inertia of one block? Can we use mr squared for those as well? That should work, right? This is just like one small object that's a single distance from the center. In general, anytime you've got an object that's just a bunch of mass concentrated at essentially one location and all a certain distance from the center, you can use mr squared for the moment of inertia. So we can still use mass times radius squared. 6 times 1 squared would just be 6 kilogram meters squared. So the rim itself has a moment of inertia of 20 kilogram meters squared. Each one of these blocks has a moment of inertia of 6 kilogram meters squared. How would we combine those to get the total moment of inertia of this whole object? Yeah, we can just add them up. Moment of inertia is additive. If you have several objects that are attached and all rotating together, then you can just add their moments of inertia individually, like calculate each moment of inertia of each object individually, and then add them together to get the total moment of inertia of this combined rotating system. So the total moment of inertia is going to be 20 plus 6 plus another 6, because we have 2 copies of that 6 kilogram object. So that'll be 32 kilogram meters squared. And this ultimately reflects how easy or difficult it is to change the rotational velocity of the object. This object, if it has a very large moment of inertia, that means it's more difficult to change how fast it's rotating, and also to change what axis it's rotating around. For example, if you have an object that's spinning and you wanted to make it spin faster and faster and faster, it takes effort, it takes torque. You have to apply torque to make it spin. But also, once it's spinning, if you want to tilt the axis it's rotating around, that takes torque also. I mean, it's difficult to tell for something like weight, but if it's heavier or spinning really fast, you actually feel a little bit of pushback when you try to tilt the axis it's spinning around. So the more moment of inertia the object has, the more difficult it is to change its rotational velocity. In that sense, moment of inertia is very much like the rotational version of mass, because the more massive an object is, the more difficult it is to change its translational velocity. The higher moment of inertia an object has, the more difficult it is to change its rotational velocity. So we often call moment of inertia rotational mass because it serves the exact same role in the formulas for rotation that mass does for translational motion. Any questions on that so far? And one of the really important differences there between mass versus moment of inertia is that typically for any given object, we don't expect the mass to change unless it breaks or unless we add something else to it, for instance. But as long as we're not breaking pieces off or adding more pieces on, this object is 17 kilograms and it stays 17 kilograms. Like resistance, it is somewhat like resistance in the sense that it's sort of a, well, I guess resistance is really more like friction. Resistance makes it difficult for current to flow. The moment of inertia doesn't make it difficult for the object to move or for the object to rotate. It makes it difficult to change the rotation of the object. So for instance, if the object is already spinning, moment of inertia doesn't make it difficult to keep spinning. In fact, it's just going to keep spinning until another torque acts on it. Torque doesn't cause rotation, torque causes a change in rotation. With a momentum change, yeah, if you change the axis, again, if you have a spinning object and you change the axis it's rotating around, like right now, this is rotating around an upwards axis. If I tilt it, I'm changing the axis it rotates around. And angular velocity has direction based on the right-hand rule. If this object is spinning like this, it's spinning this way. So if I curl the fingers of my right hand, my thumb tells me the direction of the angular velocity. This spin is associated with this upwards direction. So this would be rotating in the upwards direction. Not that any part of it is moving upwards, it's just spinning around an upwards axis. If I spin it the other way, this would be associated with a downwards direction. Or if I tilt it so it's like this rotation is now in this direction. So I'd call that, I guess that's my right, probably your left. Or if I spin it like this rotation is associated with an outwards direction, out of the screen towards the viewer. So each direction of rotation can be associated with each spin can be associated with a direction along the axis it's rotating around. So if you tilt the axis it's spinning around, you're changing the direction of the angular velocity vector, and therefore the angular momentum vector as well. Because angular momentum usually written as capital L, is angular velocity times moment of inertia. Angular velocity is a vector. It has a direction from the right-hand rule. So angular momentum also has a direction, which is the same as the angular velocity's direction. And this is actually very similar to the translational momentum. Translational momentum equals mass times translational velocity. In both of these cases, we're defining, moment of inertia, I, is a scalar. And it specifically means the level of difficulty to change the angular velocity. So these two formulas for momentum, even though they're using different variables, different meanings, they still have the same structure. In both cases, you've got a description of the motion of the object, how fast it's spinning or how fast it's moving, including direction, multiplied by a description of how difficult it is to change that motion. So how fast it's spinning, including direction, times how difficult it is to change the spin. Or how fast it's moving, including direction, times how difficult it is to change that motion. So these formulas both have exactly the same structure, even though they're talking about different kinds of motion. And the other big difference is, like I was saying earlier, the mass of the object usually doesn't change unless it's breaking or something else is attaching onto it. But assuming no braking, no attaching on, no expelling exhaust out the back as you burn fuel or something, the mass of the object is probably not going to change. But moment of inertia can definitely change. How could you change moment of inertia without changing the mass of the object? The formula for moment of inertia doesn't have V in it, but it does have R in it, yeah. If you take a look back at the formula we were using for moment of inertia, mass times radius squared, again, assuming all the mass is that same distance from the center. The mass is not going to change, but the radius can change. You can change how far from the pivot point the mass is. The rim of the wheel itself, that might be difficult to do unless it's some sort of telescoping material. But these 6 kilogram blocks you can definitely move. Like, let's say you take these 2 blocks and you move them inwards towards the center. So instead of being 1 meter from the center, let's say you move them so they're only half a meter from the center. If you do that, if you move these blocks closer to the pivot point, what would you expect to happen to the moment of inertia? We're making the radius smaller though, so what would that do? Yeah, it would be smaller. If you keep the mass the same, but makes the radius smaller, you end up with a smaller value for I. Yeah? Let's say you plug in a number for R and you calculate what I is going to be. If you then plug in a smaller value for R, the result is going to be smaller. The moment of inertia is proportional to the radius squared. So smaller radius means smaller mass. Yeah. In fact, if we try that, like we had 6 kilograms times 1 meter squared. If we try moving this to only half a meter, 6 kilograms times half a meter squared, what do you get if you square half a meter? Yeah, so we have 1/4 of 6 kilogram meters squared. And that's 1/4 of the previous amount. So if you move the block to halfway of it, or half of its original distance, you get 1/4 of the original moment of inertia, because moment of inertia is proportional to radius squared. Multiply the radius by 1/2, and you're multiplying the result by 1/4. Or let's say you move it to 5 times as far away. Multiply the radius by 5, and what happens to the moment of inertia? It's going to be much bigger. Specifically, how much bigger? You multiply R by 5, and I gets multiplied by... What do you get if you square that 5 multiplier? Yeah, it'll be 25 times as much, 25 times as much moment of inertia. Right, you're squaring the multiplier. So anytime you keep the mass the same, but modify the radius by some multiplier or divisor, that modifier gets squared when you look at how the moment of inertia changes. Multiplying the radius by some constant c means you're multiplying the moment of inertia by c squared. Any questions on that so far? And since that squared tends to amplify modifiers, that means that any change to the radius is typically going to lead to an even larger change in the moment of inertia. So changes in radius make a big difference here, changes in location. And one of the really interesting results of that, if we go back to the idea of angular momentum, what's the only way you can change the translational momentum of an object? You would change the velocity, yeah. I mean, that would be the result. But how do you do that? How do you make the translational momentum change? Right, you'd have to apply a force. So the translational momentum will only change if there's a force being applied. And what that means is it's going to change the velocity, because it's probably not going to change the mass. What would be the equivalent for rotational motion? How would you change the angular momentum? What do you have to do to an object to change its angular momentum? Exactly, you got to apply a torque, because torque is the rotational version of force. So if you apply a torque, assuming it's the only torque and doesn't get canceled out by some other torque, you're changing the angular momentum. In fact, this goes back to the same idea. The force tells you how fast the translational momentum is changing. Force is change in translational momentum over change in time. And really that should be net force. Maybe there's several forces acting on the object All we care about is the sum of those force vectors. Similarly, we can say that the net torque acting on an object, the total of all the torques, or just the torque if there's only one torque, is the rate of change in angular momentum, dl over dt. So the total force acting on an object tells you how fast the translational motion is changing, or translational momentum is changing. The total torque on an object tells you how fast the angular momentum is changing, the rotational momentum. Yeah, change in L over change in time. So what happens if there is no torque? Not that there's no L at all. Maybe the object is already spinning. But no torque means the derivative is zero. The rate of change is zero. Right, that means no change in L. It's going to be a constant, exactly. So let's assume we have a no torque situation. If we assume that the net torque is zero, maybe we set this thing spinning and then we just let it go. We just leave it spinning, assuming no more pushes on it, no friction, no air resistance, no torque at all. Then that means L is going to be constant. Let me just mark that directly under it. And this goes back to the idea of conservation. We have a conservation of angular momentum principle. As long as the torque acting on the object is zero, then angular momentum will be conserved. Or in a broader sense, if you're talking about a system of several objects that are interacting, maybe you've got spinning objects that collide with each other and influence each other's spin, the total angular momentum will be constant if and only if there's no external torques. The only way to change the total angular momentum of a system of several objects is by applying a torque to one or more of them from somewhere else. But if there's no external torque, then the total angular momentum of the whole system will not change. So let's assume that that is the case. Let's assume net torque is zero, so we get a constant angular momentum. Does that mean that these both have to be constants? No, those can change, right? And this is very different from translational motion. In translational motion, no force means no change in momentum. And of course, mass is not going to change, so velocity can't change either. For translational motion, the only way you can change velocity is by applying a force to the object. But yeah, for I and omega, this is different because I depends not only on the mass of the object, but also how the mass is distributed, where the mass is. So let's say we take a look at this wheel with a couple of blocks on it, and we take those blocks and move them closer and closer to the pivot point. As you move the blocks closer, if we move the blocks inward, what happens to the moment of inertia? Yeah, we're going to get a smaller moment of inertia. The moment of inertia decreases as the blocks move closer to the center. So what else has to happen in response to balance that out? The angular momentum can't change though, because the angular momentum only changes if you apply a torque to the system. We can pull these blocks inwards without needing a torque. Because you could have, like, let's say you've got some sort of spring-loaded spool here. Maybe these masses are attached to strings, and you've got some sort of spring-loaded spool on the axle that's pulling the masses inwards. So that's going to decrease I without exerting any external torques. But keep in mind, these need to multiply to a constant value. So if one of them gets smaller, what has to happen to the other one? Yeah, that's got to get bigger. We're going to get an increase in angular velocity. And if the angular velocity increases, if it becomes a larger magnitude, what does that mean? What's happening here? What would you observe? Yeah, the wheel's going to be spinning faster. So this is a very interesting use of this concept of angular momentum being moment of inertia times angular velocity. If you have a way of decreasing moment of inertia, if you can take some of the mass and pull it closer to the center, then that's going to make the wheel spin faster. And this is very unusual because it means you can change the speed, the spin speed, change the rotational speed of the object without needing any external influence at all. Even if this wheel is just floating in space, spinning around its own axis, far from any other things that could exert a force on it, you can change the speed of this wheel just by changing how the mass is distributed. And this can be very useful in a lot of situations. For instance, this is used in space travel. If you want to influence how fast a spaceship is rotating, like let's say it's pointing one direction, but you want it to point in another direction. Typically, if you have a spinning object and you want to change its spin, you've got to apply a torque, presumably by shooting exhaust out of some vents. You have some small engines on the sides that can be used to change rotation. For instance, if you have a rocket, presumably the main engine would be down here, applying force to change the translational motion of the object. But to make it rotate, you would presumably have some smaller engines on the sides. Those engines, as usual, apply a force to the rocket by shooting exhaust out one way to get a force in the other direction. So let's say you shoot exhaust out of this vent and also out of this vent. That means that the rocket is going to experience a force this way and also experience a force this way. What would those forces do? If you add up those forces, what's this force plus this force going to equal? Yeah, as forces, they cancel out. Because we, presumably in this case, we don't want the rocket to translationally move. We don't want any translational acceleration. So we apply forces that cancel out. But as torques, they do not cancel out. Because if we measure the torques from the center of mass as the pivot point, and center of mass is typically what an object is going to rotate around if it's just floating in space, not attached to anything. We could take this radius and this force versus this radius and this force. And if you use the right-hand rule, this radius and this force is going to lead to torque in which direction? If you put your right hand at the center of mass, the pivot point, yeah, it should be facing outwards, right? You stretch out your hand straight along the radius vector towards where the force is located, and then curl your fingers in the direction of the force. And now my thumb is pointing outwards. So that means this engine creates an outwards torque. Outwards, so we're going to draw that as an arrow pointing straight out, just a circle with a dot. And then for this one, you put your hand at the center of mass, stretch out your fingers along the radius vector, and curl your fingers along the direction of the force. And now my thumb is pointing also outwards, right? So that means the bottom engine also produces an outwards torque. The forces are in opposite directions. So as forces, they cancel out. But as torques, they're going to combine. And the reason, I mean, the forces are definitely in opposite directions, but the forces being in opposite directions and the radius vectors also being in opposite directions end up kind of canceling out. So again, take a look at the right-hand rule. You put your hand at the center of mass, the pivot point, stretch out your fingers straight along the radius vector. So from the pivot point towards where the force is located. And note that so far I can swivel my hand around, but I want to swivel my hand so I can curl my fingers in the direction of the force. And now my thumb is pointing outwards. Any other questions on that so far? So since the torques are in the same direction, they're going to combine. And overall, you get a strong outwards torque. And that outwards torque changes the angular momentum of the rocket. And since the torque, the net torque, equals the change in angular momentum over change in time. So if you turn on these side engines and leave them on for a little while, you're causing a change to the angular momentum, and that change is in this direction. We'd say it's the outwards direction, which means rotation this way. So that means these engines are going to cause the rocket to rotate like this as time passes. Or really, it's going to make it rotate faster and faster. Or if it was already rotating this way, turning on these engines would slow it down and bring it to a stop. So you can use these side-mounted engines to change the rotation of the object, the rotation of the rocket. And this is very useful because you want to be able to tilt the rocket in any direction you want, so you can turn on the main engine and get a large thrust in the correct direction to change your maneuvering. How the top torque is outwards? Yeah, if you put your hand at the pivot point, stretch out your fingers along the radius vector, and notice that my fingers stretch straight along the radius vector. I can still swivel my hand around, but I want to be able to swivel my hand such that I can curl my fingers in the direction of the force itself. So radius, straight, and then curl fingers in the direction of force. The only way I can do that is by having my thumb pointing straight outwards. Also, before you even apply the right-hand rule, a good thing to think about is that the torque is always going to be perpendicular to the radius vector and perpendicular to the force vector. So radius vector and force vector, those two vectors together, radius and force, form a plane. The torque vector is going to be perpendicular to that plane. The only options perpendicular to this plane are either this direction or this direction, in this case, straight out or straight in. So just from those perpendicular properties, that the torque has to be perpendicular to radius and perpendicular to force, in this context, we can narrow it down to outwards or inwards torque. The right-hand rule is just to choose one of those two. And that's true for other right-hand rules as well. Later on in 7C, we're going to look at some right-hand rules for dealing with magnetism. And those are also going to be situations where you can narrow it down to two possible directions based on perpendicular properties. And then the right-hand rule is to just choose one of those two directions. Any other questions on that so far? Over the summer, I don't do workshops, but I do have extended office hours. So in this case, we are using the engines to change the rotation of the rocket. And yeah, during fall, spring, summer, or fall, winter, spring, I do workshops for all the 7 classes. And this is a fairly powerful approach. You're directly applying torque using the engines. You can apply a very strong torque because you can have these engines be very strong. But what's the disadvantage of using these engines? What do you have to expend in order to, like every second you have the engines turned on, what do you have to use? You're expending energy, yeah. And where is that energy coming from? Right, the fuel. So you're expending energy, you're using up fuel, and that's a limited supply. And yeah, it's money, and this fuel is expensive. But this is a limited resource. Even if you got all the money you have, all the money you want in the bank back on Earth, if this rocket is out in space, then all you have, your entire world, is just what's inside the rocket. You can't just, like, I don't know, email some extra fuel to the rocket. So the fuel is limited. This is a very limited resource. You want to only use the engine jets to rotate when absolutely necessary. But there's a way to do this. Yeah, there are ways to email some things. You can email information. You can say, like, email the instructions on how to 3D print a wrench, and then they can print it out if they have a 3D printer on board. But of course, they only have as much physical objects as are already there. But for fuel, it's limited. You can't just wish for more fuel. But using this idea of angular momentum being moment of inertia times angular speed, you can modify the rotation without spending fuel using this principle. If you can find some way to decrease your moment of inertia, then you can increase your angular speed. Like, let's say you're already spinning in the correct direction, but you want to spin faster. How would you make this rocket spin faster? Yeah, you've got to decrease the moment of inertia. And you do that by moving some of the mass closer to the center. So if this rocket has, one way to do this is to build extra mass into the rocket that's on motors and can be moved around inside the rocket. So let's say you have a bunch of mass on motors and like on tracks inside the rocket that's further out towards the ends, and you're spinning at a slow speed, but you want to spin faster. You can use the motors to pull the mass inwards towards the center, and then the rocket's going to spin faster. Or if it's spinning too fast and you want to slow it down, you just move those masses further out towards the edges, and it's going to slow down because increasing R increases the moment of inertia, and increasing the moment of inertia decreases your angular speed. So there are ways to modify how fast you're spinning You can't get started in the first place like this. You can't change a 0 to anything other than 0. But if you're already spinning, you can modify your moment of inertia to change how fast you're spinning. So and this is very useful because it doesn't cost fuel. It does cost energy. You've got to spend energy to move these masses around. But if these are electrical motors, you're just using electrical energy, and you can get as much of that as you want for free if you've got solar panels on the rocket. So this provides a very useful, sustainable way to change the rotation of the rocket. And yeah, this is one of my favorite things about space travel and just design, the idea of designing stuff like this in the first place is that it uses so many different branches of science. You've got to bring in the mechanics in order to understand the idea of torque and force and maneuvering the rocket around. In order to actually accomplish this, you've got to have fluid flow to move the fuel around and make sure the right amount is getting to the engines at the same time. And to design the fuel itself, you need lots and lots of chemistry to make sure it's burning at the right rate. You've got to have thermodynamics to make sure it doesn't overheat. You've got to have all sorts of biology to make sure the life support systems work. It's an amazing way to just bring together lots and lots of different fields of study and put them in this extremely challenging environment and make sure they work. And this is just one small glimpse into the many things that go into that. Any other questions on that so far? And this has a lot of other examples in a more literally down-to-earth fashion as well. What's another situation where you might have something or someone spinning around and want to change how fast they're spinning? Yeah, a merry-go-round, for instance. If you've just got like a playground merry-go-round that's spinning around, you've got some kids on the outer edge. If they walk further towards the center, what's going to happen? And yeah, a tire swing as well. If you've got everybody, like let's say you're in a tire swing and it's spinning around, but let's say you lean outwards. What would you expect to happen? Right. If everybody on the tire swing leans outwards, then it's going to slow down. You've increased the overall radius. And of course, the formula won't be this simple because not all the mass is at one distance. But in general, if you bring some of the mass further out, you're increasing the moment of inertia. If you bring some of the mass closer in, you're decreasing the moment of inertia. Yeah, I mean, this is typical playground play anyway, right? You swing around on the tire swing, have everybody lean out, it slows down, have everybody lean in, it speeds up. Lots of stuff on the playground is very closely related to this angular momentum physics as well. Or let's say you just jump and do a spin, most commonly seen in figure skating and diving. If you jump into a spin, you leave the ground, and yeah, ballet as well, and some parts of gymnastics. If you jump off the ground and start spinning, you're applying a torque as you leave the ground because you're pushing off of the ground. So by pushing off of the ground, you can make yourself start spinning because you've got a torque. But as soon as you're in flight, you're no longer experiencing any torque at all because you no longer are pushing off of anything. You've got gravity pulling on you, but gravity's pulling on your center of mass. So radius is 0 and you get no torque. So how do you modify how fast you're spinning while you're in midair? Yeah, assuming the angular momentum is constant, decreasing the moment of inertia causes an increase in angular velocity. And likewise, increasing the moment of inertia causes a decrease in angular velocity. Because if two things multiply to a constant, then they have to be changing in opposite ways if they change. And yeah, you can change the distance, specifically the distance the distance of how your mass is distributed. And typically the easiest way to do that, like if you just treat your body as sort of a cylinder, if you have your arms outstretched, you've got some of your mass further out. So let's say you go into a spin jump with your arms outstretched, but then you pull your arms in close to your chest. What happens to your moment of inertia if you pull your arms in closer to your chest? You're making the distance smaller though, so what's going to happen? Yeah, smaller distance because you're tucking your mass in closer to the center. Smaller distance on average means a smaller moment of inertia overall. And smaller moment of inertia means faster angular speed. So if you jump off the ground and spinning as fast as you can with your arms outstretched, pull your arms in, and you spin even faster. So this is the way that expert ballet dancers and figure skaters and divers and gymnasts can go into extremely fast spins that look like impossibly fast. You leap off the ground with as fast a spin as you can, and then pull your mass in towards the center to spin even faster. And then, of course, when you're about to land, you stretch your arms out again, which does what? Yeah, you're going to slow down again, because you don't want to hit the ice or the diving board, or not the diving board, the ice or the pool or the balance beam or whatever at high speed. You want to slow down so you can get a more controlled landing. So that's using this exact same principle. Change your radius, change the average radius of some of the mass to change the overall moment of inertia, and changing the moment of inertia allows you to control your angular speed. It doesn't allow you to change the direction you're spinning. You're still going to be spinning around the same axis, but you can make enormous changes in how fast you're spinning. This same principle is also a big part of how cats are able to rotate as they fall and make sure they land on their feet. By messing around with their mass, by just moving their legs further in or out and twisting around their spine and their tail, they can modify to some extent how fast they're rotating and make sure they're rotating in a way that touches down mostly on their feet. Yes, very smart. And in general, anytime you want to change how an object is rotating after it has left the ground, this is the way to do it. Any other questions on that? And let's try running a quick calculation then. Because so far we've been just using mr squared for moment of inertia. But let's see what happens if it's not just a mass at a single location. Let's say instead of just a single point or a rim of a wheel, let's say we have a stick, a heavy stick whose mass we cannot ignore. And let's say its total mass is m, and let's say its total length is L. So, and I'm going to use a lowercase cursive L here because I don't want to get it mixed up with the capital L for angular momentum. So lowercase cursive L, so we don't get it mixed up with an I or a 1 or something, is the length of the stick. And let's say we are holding it on one end and allowing it to rotate around that one end. So the end of it is the pivot point. And let's say we want to calculate the moment of inertia of this entire stick. Can we use the mass times the length squared? Is that going to work? Can we say that, actually, if we do use mass times length squared, what are we assuming about the location of the mass? It's all the same, right? If we just say mass times length squared, we're assuming that all the mass is at this distance. But yeah, it's not all at this distance. The mass isn't all L meters away from the pivot point. That would only be the case if this were like a very lightweight stick and we had a large heavy ball on the end of it. Then we could use mass times length squared. But in this case, the mass is more spread out. The whole stick has mass. So some of the mass, a little tiny bit of the mass, is at a distance of L. Some of the mass is at distance half of L or 3/4 of L or 1/4 of L. Some of the mass is even at almost distance 0. So the fact that the mass is spread out at various different distances means we can't just use the mass times one single distance squared. What we can do instead is imagine splitting this stick into smaller pieces. Let's say you look at this piece and this piece and this piece. If we split this into tiny pieces, each piece can be treated as almost a point mass. Because if you look at, for instance, this piece is a tiny bit of mass. And that tiny bit of mass, let's call dm. We usually use d in calculus to mean a tiny piece of something. So dm means this tiny piece of mass. And that tiny piece of mass is some distance from the pivot point. Let's call this distance x. So we've got a tiny bit of mass, some distance from the pivot point. And to calculate the moment of inertia there, we would say moment of inertia of that tiny piece. That can be treated as a single point. So we can say that its moment of inertia is mass times distance squared. Mass, a tiny bit of mass, times not the whole length, but just this distance from the pivot point squared. And of course, x I'm going to leave as a variable because we could be talking about any one of these tiny pieces. So this tiny piece, distance from the pivot point squared times the tiny bit of mass. That'll be the moment of inertia of that tiny piece. And we can do that for any of these tiny pieces. This tiny piece is this distance times that tiny, or this distance squared times the tiny mass. Because the moment of inertia of a point mass is, yeah, exactly. X is taking the place of r here. It's just the distance from the pivot point. And in general, moment of inertia of a tiny bit of mass is the mass of that tiny piece times distance squared. dm just means a tiny bit of mass. And this is the same d that you see in integrals and derivatives notation. D just means a tiny piece of. It's essentially like saying delta m in the sense that as you go further and further out, you're adding more and more mass to the stick. But if we're talking about a very small extra bit, we call it d instead of delta. Same idea. Formally it's a limit. D something is basically the limit of delta something as we look at smaller and smaller pieces. So that would be the moment of inertia of each tiny piece. But how do we find the total moment of inertia if we've got a formula for each little bit of moment of inertia? Yeah, we use an integral to add them up. We're adding up this tiny piece plus this tiny piece plus this tiny piece and so on. And an integral literally just means adding together all those tiny pieces. So the total moment of inertia is the integral of x squared dm. That's literally all the integral sign means. Yeah, this stylized curve here, this is literally supposed to just be a stylized s. S for summation. The integral signs literally just means add up this value over a bunch of tiny pieces. You're adding up a bunch of tiny bits of moment of inertia to get the total moment of inertia. So that means we just need to find a way to integrate this. The only problem is x and m are different variables. We need some way to rewrite this using the same variable. And to do this, we can use the idea of density. If we assume that the stick is uniform density throughout, like every tiny bit is the same density. If we go back to the idea of density, how do we usually define density? Yeah, mass over volume. In this case, though, we don't really care about volume. We really care more about length. So let's use what we call linear density, which is mass over length. And we could look at this as the mass over length of the whole thing. So the total mass divided by the total length. But if we're assuming uniform density, then the total mass over the total length should be the same as the mass of any piece divided by the length of that piece. So if we take a look at this tiny piece, it has mass dm, and its distance would be a tiny increase in x. So if x is the distance from the pivot point to this object, this tiny piece, the length is going to be a tiny bit of extra x, which we would call dx. So if x is the distance from the pivot point out along the stick to the location of interest, dx is a tiny bit of extra length, such as in this case, the length of that tiny piece. So the linear density of this tiny piece would be tiny mass over tiny distance, dm over dx. So the density of the whole thing, total mass over total length, should match the density of any tiny piece, dm over dx, tiny bit of mass over tiny bit of length, because we're assuming the whole stick is the same density. We can then solve for dm. If you isolate dm here, what do you get? Well, we got to get rid of the dx. So let's multiply both sides by dx. And we get dm equals big M over L times dx. And now we can make this substitution. Everywhere we see dm, we can replace it with big M over L dx. And also we need limits of integration. What's the smallest value of x and what's the largest value of x? What piece of mass is, what's the closest to mass, a bit of mass can be to the pivot point here? Yeah, smallest x is 0. We've got bits of mass all the way up to the pivot point itself. So we should start the integral at 0. And also the bits of mass can go all the way out to what largest distance? We don't have an infinitely long stick though. The stick stops at what distance? Yeah, the stick stops at the length, L. So the furthest bit of mass is L away from the pivot point. So the smallest value of x is 0 because we have mass all the way to the pivot point. The largest value of x is L because we have mass all the way out to the end of the stick. And now we can integrate this. M over L is a constant, so we can pull that out. Anyone remember what the integral of x squared should be? The derivative would be 2x, but what would be the integral? You're going in the other direction for integrals, the antiderivative. For the derivative, you decrease the exponent. For the integral, what would you do instead? Yeah, you get an x cubed because you're increasing the exponent. And yeah, also a divided by 3 because you'd have to divide by the new exponent. The idea is we want a function whose derivative would be x squared. Derivative of x cubed would be 3x squared, so we also need to divide it by 3 to balance that out. And that's evaluated from 0 to L. We don't need a plus c because it's a definite integral. Plug in L here, we get m times L cubed over L times 3. And then we plug in 0, we get nothing, so we don't need to subtract anything. But what can we reduce here?
The top would be L squared.
Right. We can reduce one of the L's there. We just get mL squared over 3. In other words, the moment of inertia for this stick is 1/3 times mass times length squared. So we notice that it still has mass times distance squared, specifically the mass of the stick times the length of the stick squared, but it also has this fractional multiplier, this 1/3, accounting for the fact that the mass is not all out here, the mass is more distributed throughout the entire length. Yeah, this is exactly where these formulas come from. And of course, now that we've got that, we don't have to go through all these integrals every single time. In general, if you have a stick that's rotating around its own endpoint as the pivot, you can just say its moment of inertia will be 1/3 times mass times length squared. And each shape, each way the mass could be distributed has its own formula. And of course, typically in an example, like if you're actually trying to figure out what's going on in a rotational situation, you wouldn't work out the moment of inertia formula from scratch. You'd presumably look it up on a data table if it's a standardized stock shape that's already known. Like you can look up on a data table moment of inertia for a solid sphere or a hollow spherical shell spinning around its own axis, or a stick rotating around its own endpoint is just a 1/3 mL squared. Rotating around its own center is going to be a different fraction. Or if you've got a cylinder or a disc, any shape that's typically used in rotation, you can probably look up a formula. And it's always going to be some fraction times a mass times a distance squared. But what fraction that's going to be is going to depend on the exact shape. And yeah, breaking it down step by step, I think is very useful in cases like this. Look at it a little bit at a time. In this case, a little bit of mass at a time, or a little bit of math at a time. But also look for connections to the previous math classes you've taken. All that stuff about derivatives and integrals you've seen in calculus classes, derivatives are all about how something is changing as time passes, or how something is changing from location to location. Like dm dx, the density, that's a derivative. How much the mass is changing as you go further and further out on the stick. And anything about integrals are just about accumulating something as you go along. How much moment of inertia we're accumulating as we make the stick longer and longer. That's really what integral dx is all about. How much extra moment of inertia we're accumulating per meter of extra stick length. So keep that in mind as you go forward. Integrals are all about accumulating stuff as you go on. Derivatives are all about how fast is something changing. You're welcome. That's it for today. So I will see you next time.